been sitting and listening and getting inspired and hearing about the great stuff that other people have been doing. But now I want you to do something. So if you would please, try to draw or imagine the monster that I describe. This monster is kind of like a horse, just it's made out of spaghetti, so its face and its legs are all long and wobbly. Also, it has a rectangle body that's covered in hair and a long, skinny spaghetti tail with a puff of fur just at the end. This monster is also huge. It's so big, you could fit a castle full of people on its back, and it would still be able to frolic around the Alps, no problem. I'm curious, does the monster you're imagining look a little bit like this? This image is from a speculum, a kind of medieval encyclopedia that was made in the 1480s. We instantly recognize this weird, huge, stretched-out horse monster as an elephant. But it's also pretty obviously not an elephant. What you drew or imagined based on my description of a spaghetti horse is probably not an elephant either. But imagine you've never seen an elephant before. Imagine you've only heard about them or read descriptions of them. We construct the image of this beast based on abstract ideas and relationships to things we know and understand, like animals we have seen, basic shapes and relative sizes. It's imprecise. I mean, look at it. It's not really an elephant, but it is kind of. While this image may not be entirely accurate, it conveys key information about its subject, enough that we understand it's an elephant. And as importantly, the story that it tells reminds the medieval viewer that the world is much bigger and much more marvelous than previously imagined. The next image that I want to share with you is from a very different space and a very different time. I took this image using a scanning electron microscope. I think the technology behind this is absolutely amazing, and this speck of dust suspended in glue looks really cool, considering we don't usually get to see what nanometer-sized stuff looks like. But does it move you? My guess is probably not. While the medieval drawing lacked scientific accuracy, my image lacks artistic vision. But when art and science fuse, we are able to communicate ideas about the mysterious unknown and understand it more clearly. I want to share a love story with you, the story of the deep connection between art and science and our connection to these subjects we work with. I use the word love because it's the only one that I know that communicates the weight and depth of connectedness. I want the work that I do to represent this love story. I want to communicate both artistic and scientific ideas. I have a lot of room for improvement, and as you may not have yet noticed, I am quite young. But I think by celebrating the mathematics, technology, and science that facilitate my art, I draw closer to an elegant fusion. This is a painting I made using a graphics tablet and painting software. I made this hoping to make you feel uncomfortable. Look at that hand. It looks kind of like raw meat, red and visceral. But really, that texture is just super realistic, out-of-place pomegranate. I'm trying to tug at your emotions by presenting both reality and abstraction, peeling away the surface and asking questions like, what are we really made of? Is there that significant a difference between my flesh and a pomegranate seed? We're all the same collection of atoms and stardust in the end, right? But the science in my art doesn't stop at concept. Classic art tricks like the golden mean and rule of thirds are actually just geometry. That deep red of the grapes and bright pop of green in the stems is a product of contrasting colors in color theory, and Also of the varying voltages applied to pixels in the liquid crystal display of your computer or TV screen. When I paint, my hand moves like it would when I'm using traditional paints. The surface of my graphics tablet emits a magnetic field that can detect my pen location. Sensors in the pen's tip say how hard I'm pressing, and a gyroscope what angle I'm pressing from. Complex and beautiful algorithms translate all of this data into simulated paint and ink. Now, you've seen what my art looks like. I want you to try and draw or imagine again. Since I'm talking about the fusion of art and science, I want to tell you about some of my favorite physics, nuclear fusion. So first, I'll tell you the story of one step in the nuclear fusion process, and then we're going to make a picture. In stars, like the sun, there's a lot of hydrogen, which is made out of one positive proton. There's also a lot of deuterium, which is one positive proton stuck to one neutral neutron. Protons, which are in both hydrogen and deuterium, are kind of like the north sides of a magnet. Put two north sides of a magnet together, and they resist each other. Same with protons, just protons hate each other a lot. I would need to heat this room up to at least 15 million degrees Celsius. Don't worry, I do not yet have that capacity. And I would need to be many quintillion times stronger in order to smash two protons together, like I push the north sides of a magnet together. But the sun is so big and so hot that the forces in its core can smash protons together. Under the pressure of gravity, deuterium and hydrogen get pressed and pressed and pressed until they snap together in a huge burst of light. And together, their fusion creates a brand new atom, helium. They stay together because of something called the strong force, or the strong interaction. I like to think of the strong force being kind of like a pair of hooks. You press the protons together, and once they're hooked, they can't pull apart, even if they're trying. All right, now we understand the story. Let's make a picture. We have one proton-neutron pair, deuterium, and one proton. We push them together inside of our star, and they fuse, producing helium-3 and a big flash of light. Now, this is a pretty good picture, and it adequately describes the story of nuclear fusion that I just told you. But like the elephant the medieval scholar drew, this image is a feat of imagination. Light isn't really a bunch of wiggly lines, and atoms aren't really just circles. In fact, thinking of atoms like circles can really inhibit our understanding of them in other physical contexts. Nevertheless, the flexibility of art allows us, in this instance, to imagine the physics that makes stars shine. It helps to imagine and draw a picture for several reasons. First, because we're rephrasing difficult ideas in known stuff. By using metaphors like magnets and hooks, we can come to an intuitive understanding of this conceptually difficult physics. As a visual artist, I've focused on visual art connections, but music and performance arts are equally as capable of moving and shaking in tune with science. By communicating scientific ideas in the languages of art, we can teach and learn better, connecting the visual, auditory, and kinesthetic learners. The last image I want to share with you today is an inspiring chapter in the physics love story, and I think it embodies that marriage of technical and emotional intelligence that I aspire to. This image was taken in 1990 by Voyager 1. As the Voyager spacecraft reached the edge of the solar system, ground control ordered it to turn around and take a photograph of each of the planets it had visited. This is the picture of Earth, which appears just as a faint dot suspended in a sunbeam. Carl Sagan gave a beautiful speech about this image. It's the pale blue dot. But what makes it special? I chose this to represent a perfect fusion of art and science. First, because that's us. That's where we live. It's a true and accurate representation of our planet brought to us through technology and scientific skill. And second, because they didn't have to look back. This image, although important and technically marvelous, is probably less scientifically informative than, say, another picture of Saturn, or some other pretty faraway, mysterious thing we've never seen before. But the scientists and engineers on the Voyager project had the insight to look back and provided us with this important, accurate, humbling portrait of ourselves, a portrait that asks and inspires some of our deepest and most existential questions about our place in the universe. Our actions as scientists and artists shape the world that's watching. This is emotionally intelligent science. It's scientifically intelligent art. Admiring the fusion of art and physics is good. Doing it is even better. So let's not be quiet about it. For most of my life, I firmly believed I wasn't cut out to be a scientist. I wasn't hooked to physics as a kid, and I wasn't a math whiz in junior high. Rather, I fell in love with physics because Professor Michael Broidy told a classroom full of arts and humanities students, of whom I was one, that creativity and abstract thinking are what make a truly great scientist, something I had never imagined to be true before. Simply by talking about the science in art and the art in science, we can help to inspire more people to make the connection. And now, as I set out on the long journey towards my goal of a Ph.D. in physics, I want to celebrate the creative in me. I want to be the kind of physicist who thinks like an artist, develop both my technical skills and artistic vision, because that vision is equally as important in doing great science. Physics isn't just about the XYZ. It's not just about finding that one true and perfect answer. Rather, like art, it's about wiggling our way through complex abstractions while doing our best to piece together a communicable idea that makes enough sense to do something more with it. And knowing a little about the mystery can only make it more marvelous. Thank you.